So we ended the last video in a situation where atoms didn't quite act like they would have predicted. Specifically, instead of making 3 bonds and having 2 lone pair non-bonding electrons, like we would have predicted based on its dot structure, nitrogen made 4 single bonds. Sometimes structures don't quite act like we would expect them to, especially if there is a charge involved in the structure. So what we need to do is to find a better way to check our answers. We can do this through calculating the formal charges of the atoms within our Lewis structures. So what is a formal charge? The formal charge is the charge carried by an individual atom within a molecule or ion, assuming that all the atoms are shared equally through bonds. We know this isn't true, but we suspend this knowledge because it's just easier this way. The question then becomes, how do we calculate formal charge? Well, we take the number of valence electrons an atom starts with. Then we subtract the number of non-bonding or lone pair electrons, and then we subtract 1/2 of the bonding electrons. With Lewis structures, our priority is to make sure that every atom has 8, or 2 if you're hydrogen, valence electrons. Once that is established, formal charge is super important because it helps us check the Lewis structures that we make, especially in situations where atoms don't act like we would predict based on their numbers of valence electrons, or as we'll see in class, in resonance structures. Just a quick note that when atoms do act like we would predict based off of their number of valence electrons, they have a formal charge of 0. The principles of working with formal charges, outlined in letter B here of the skeleton notes, is that the formal charges of atoms within a molecule must add up to match the overall charge. We want to minimize the magnitude and number of charges on our molecule. So 1 charge atom is better than 3 charges on atoms, charges on 3 different atoms, whereas a charge of -1 is better than a charge of -3. There are also rules for where charges should go within an atom. For instance, we want to put negative charges on more electronegative atoms because they're better at pulling on and holding on to negative charge, whereas we'd prefer to see positive charges on less electronegative atoms. In Lewis structures, we will never put a charge on hydrogen. Yet. So let's practice. We've already worked through the structure of CO2. It's a carbon double bonded to an oxygen on each side. Use your new skills to calculate the formal charge on each atom. So go ahead, pause the video and practice. So for oxygen, we start off with 6 valence electrons. We subtract the 4 electrons that are non-bonding electrons that are hanging out in the lone pairs, minus 1/2 times the number of electrons in bonds, which is 4. That gives us 6 minus 4 minus 2 equals 0. Then for carbon, we start with 4 valence electrons. We have no lone pairs, so we just subtract 1/2 times the number of electrons in bonds, which is 8. So that gives us 4 minus 4 equals 0. So for all 3 of our atoms, we have a formal charge of 0. 0 plus 0 plus 0 equals 0, which is equal to the neutral or 0 charge of our molecule. Okay, so why do we need formal charge then? Because I just gave you an answer where it didn't really seem to matter that much. Well, we're going to try with a molecule that's slightly different, ozone, or O3, which has a linear structure. So why don't you pause and take a guess at what the structure of ozone might look like? Okay, so we have 3 oxygens. And so if oxygen has 6 valence electrons, 3 times 6 gives us 18 valence electrons to work with. So if we draw out our oxygens in a row, we start by creating a single bond between each oxygen. That takes away 4 electrons, which gives us 14 electrons to work with. We can start by taking away from the leftover electrons and put lone pairs on each of the outside oxygens, so 3 lone pairs, until we fill them. Okay, so we've added 12 electrons to our structure, so we subtract 12 from 14, and that gives us 2 electrons left over. Okay, so where do we put those leftover electrons? We have extras. Again, like we did with nitrogen in NH3, we put a lone pair on the central atom. So right off the bat, this structure does not look right. Why? Well, because one of our oxygens, specifically the central oxygen, does not have a complete octet. But to be safe, let's go ahead and practice calculating the formal charges here. We end up with a charge of -1 for each of the outside oxygens and a +2 for the center oxygen. So they add up to equal a neutral molecule. But right away, this should make us uncomfortable because every atom has a charge, which is generally something we don't want to see. And one atom even has a charge of +2. So let's try again and see if we can get our charges down. So one thing that we can do is to take one of the lone pairs on the outside oxygen and turn it into a double bond with the central oxygen, as we've done here over on the left. So we've kept our total number of electrons the same, but now our central oxygen, thankfully, has an octet. So let's go ahead and do the formal charges. For the oxygen with 2 bonds, we have 6 - 4 - 2 = 0. For the central oxygen, we have 6 - 2 electrons in lone pairs minus 1/2 times 6 electrons in bonds equals +1. And then finally, for the oxygen with 3 lone pairs, we have 6 - 6 - 1/2 times 2 gives us -1. So this molecule may not look right because the central atom is making more bonds than we would predict based off oxygen's electron configuration. However, this configuration is valid because -1 plus +1 plus 0 gives us 0 for a neutral molecule. But also, each of our oxygens has 8 electrons. We have 2 charges instead of 3 charges, and both the charges have a magnitude of 1. We also can draw the same structure but going on the opposite direction, where one of our oxygen on the left would have 1 charge instead. And we could go in, when we have these non-zero formal charges, we want to go in and write the charges on the molecules, or we can write the charges on the atoms when they're not 0. There we go. So let's do one more practice. So why don't you go ahead and try this on your own? This is for the cyanate ion, or OCN-. The structure is linear and the atoms are written out in the order that they're arranged. Remember, the least electronegative atom goes in the center, and carbon usually goes in the center anyway because it makes 4 bonds. So go ahead and try it. Okay, so we start by adding up the valence electrons. 6 from oxygen plus 4 from carbon plus 5 from nitrogen plus 1 from the -1 charge for a total of 16 electrons. We draw the skeleton in the order of the formula, O, C, N, and then connect them with single bonds. So that's 4 electrons, and we subtract 4 from 16 to give us a total of 12. So the next step is to fill all the octets. That takes 12 electrons, and we're left with 0. Let's take a look at this structure. Okay, so right off the bat, this should make you uncomfortable because carbon only has 4 electrons. It's missing 4 electrons and needs to make 2 more bonds. And we always want our atoms to have have 8 electrons or 2 of your hydrogen. And carbon's always going to make 4 bonds no matter what. So for carbon to make a complete octet and to have those 4 bonds, we need 2 more. So where do those bonds come from? Well, pause and think about it. So we know that oxygen likes to make 2 bonds, so we can take one set of lone pair electrons from oxygen and add them to make a bond with carbon. We still need 1 more bond with carbon though. So where can we get it from? Well, one place we can take it from is nitrogen, just like we did with oxygen. Okay, so we still have 16 electrons, and now everyone, oxygen, carbon, and nitrogen, have an octet. So let's go ahead and check with formal charge. So for oxygen, 6 minus 4 electrons in lone pairs minus 2 electrons, 1/2 of the electrons in bonds gives us 0. For carbon, 4 valence electrons minus 4 electrons in bonds gives us 0. And then finally for nitrogen, we start off with 5 valence electrons minus 4 electrons in lone pairs minus 1/2 times 4, or 2 electrons in bonds gives us a charge of -1. Alrighty, so if we add up these charges, we have 2 neutral atoms. Only one has a charge. And so we check out there. But there's one more factor we have to consider, is to figure out if this is the spec structure, and we need to go back to our rules. If we have a negative charge, we want it to go on the most electronegative atom. Is nitrogen the most electronegative atom in our structure? No, it's oxygen. So let's try redrawing our structure again over here on the left. We can give one of the CO bonds back to oxygen to give it 3 valence pairs, three lone pairs. And instead of having a double bond, we can make a triple bond between carbon and nitrogen, and then nitrogen has 1 lone pair. And remember, nitrogen prefers to make 3 bonds anyway, although we now have oxygen making 1 less bond that it would like. So for oxygen, we get 6 minus 6 minus 1 equals a charge of -1. Carbon, 4 minus 4 equals 0. And then for nitrogen, 5 minus 2 minus 3 gives us 0. So we've got -1 again, and we have 1 charge on 1 atom, but this time it's on the oxygen, which is more electronegative. So this structure already is looking better than the one we saw in the center. But it turns out there's still one more structure that we could write, and that's with O and C having 3 bonds, and carbon and nitrogen having 1 bond. But in this case, for oxygen, we would add 6 minus 2 minus 3 equals +1. And for carbon, we would still have a charge of 0, but for nitrogen, we would have 5 minus 6 minus 1, which would give us a charge of -2 for nitrogen. This structure is unfavorable because we have a plus on the most electronegative atom and a minus on the not most electronegative atom. We have charges on multiple atoms rather than 1 compared to the other structures, and we have a more than +1 charge on the whole, and we have an atom where we have a charge with a magnitude greater than 1. So which of these structures is correct? Well, that's where we're going to pick up in class. I'll see you soon. Bye.